Okay, so for problem number 20, we have this geometric series here, and we want to find out if it's convergent or divergent. So if it converges, it must mean that the limit of this ratio to the power of n, as n gets super large, is 0, because with this infinite series, you're going to keep adding these terms. And the only way that the sum can ever go to somewhere and stay near a fixed number is if the terms that you're adding, they're essentially 0, because then they don't change your sum, and therefore your sum converges, right? So we want to see if the limit of r to the power of n is equal to 0. And that can only happen when the absolute value of r is less than 1. Because if you take a number that's less than 1, if you raise it to infinity, it essentially goes to 0, right? Whereas if you take a number that's more than 1, if you raise it to infinity, that number is just going to grow without bounds. So our series looks like this, and we already know that it is a geometric series, like it tells us, right? So what that means is that there is multiplication involved. So at first, you may struggle to see the pattern, right? You may see these 4 numbers, and you say, okay, what is the next one? I don't get it. However, the trick is if you look at the first one, you already know that all of these are going to be multiplications of 2, because if 2 is there, it has to be multiplied, right? Because the whole idea of a geometric series is that it's successive multiplication. So let's turn this into fractions. So 2 is the same thing as just 2 over 1. 1/2 is the same thing as 1 over 2. 0.125 is the same thing. That's going to be 1 over 8. This is going to 0.03125 is the same thing as 1 over 32, and so on and so forth. Now, if we put it like this, something interesting emerges. We can see that these are all powers of 2, right? However, actually, maybe let me put it like this. So this is 2 to the power of 1. This is going to be 2 to the power of minus 1. 1 over 8 is going to be 2 to the power of minus 3. 1 over 32 is going to be 2 to the power of minus 5. So it appears that it's powers of 2. However, it's the odd numbers that are in the exponent, and they're negative. So from this, we can conjecture that the next one's going to be 2 to the minus 7, and then 2 to the minus 9, and so on and so forth. So once we have very clearly seen the pattern, we're now ready to write out the formula. So this is going to be a sum from 0 to infinity, and it's going to be 2 to the power of n. However, that's not quite right, because if I plug in, say, 0, which is our first index, we're going to have 2 to the power of 0, so it's not there. So it definitely means that I have to do a plus 1, because now if I plug in 0, which is the first index, right, it's going to go 2 to the power of 0 plus 1, which is 2 to the power of 1. So we still do need to change a couple of things. Well, the first thing is that these terms are decreasing, like they're getting more and more negative, right? So I do need to have a minus here to account for it being negative. And we can see that from each index, it skips 1. So from 1 to minus 1, and then from minus 1 to minus 3, from minus 2 to minus 5. So it actually means that it's 2n, right? So we're going to have minus 2n and then plus 1. And let's just see if this works out. So 2 to the minus 2n plus 1, if we plug in 0 for the first index, that's going to be 2 to the 0 plus 1. And then if we plug in 1 for the second index, it's minus 2 times 1, minus 2 plus 1 is going to be minus 1, right? And then if we plug in 2 for the second index, is going to be minus 2 times 2, so minus 4 plus 1, minus 3. If we plug in 3 for the third index, we're going to have minus 2 times 3, so minus 6, plus 1, minus 5, and we can see that this perfectly works out, right? So all we have to do here is we still have to adjust it, because we want this guy to look like this. So we want it in the form of a times some number to the power, or some ratio to the power of n. So we're just going to adjust this a little bit. So that's 0, infinity. Oops. And I'm just going to say that's 2 to the minus 2 all over n, right? And then times 2 to the power of 1. Because all I've done here is I've broken down these exponents, right? And maybe I should explain that a little bit more. So 2 to the minus 2n plus 1, that's going to be the same as 2 to the minus 2n times 2 to the power of 1, which is the same thing as 2 to the minus 2 to the power of n times 2 to the power of 1. Okay, so once we have established that, I'm just going to move this 2 to the power of 1 and just put it in front, just so that we can easily compare it, right? And we can now see that this is in proper form right here. So once we have seen that, we can see that a, which is the constant that goes in front, so a is equal to 2, and r is equal to 2 to the minus 2, which is the same thing as r is equal to 1 over 4. So we have that for it to be convergent, the absolute value of r, let me erase this, the absolute value of r has to be less than 1. And so we have that the absolute value of 1/4 definitely is less than 1, so it converges. Right? And then once we know that it converges, all we have to do now is to find the value of this sum, this infinite sum. And so the formula for the infinite sum is a over 1 minus r. We have a here and we have r here, so all we have to do is plug it in. So Sn therefore is going to be 2 over 1 minus 1/4, which is the same thing as, that's going to be 2. 1 minus 1/4 is 3/4, and so that's going to be 8 over 3. And this here is the value for our series, and that's it for this problem.